All right, our notes for today, we are going to be talking about key features for our graphs. Now, these key features are going to be applied in this unit in our functions. We're going to talk about it when we get into our quadratics, because quadratics, they are a function. We're going to talk about them when we're dealing with our polynomial unit, because again, a lot of our polynomials are also functions. So we're going to keep going back and keep cycling back to these different key features here. These are also going to become vocab cards. So if you want to go ahead and after you're done with the notes as another way just to kind of go through the definitions again, if you want to go through and start those vocab cards already, you are more than welcome to, because you're going to have to do them eventually anyways. So these are the ones that we're going to talk about. Increasing, decreasing, positive, negative, max, min, end behavior. These are all topics that you did talk about in Algebra 1 before. So I am hopeful that once I say them again, it'll kind of be like, oh yeah, I remember hearing that stuff before. Even and odd functions, continuous, discontinuous. Even and odd, that's going to be new, but continuous and discontinuous, we did start talking about that with our piecewise functions, how our piecewise functions are discontinuous. And we can talk about the exact spot where they're discontinuous, because that's where you have your jump in your graph. So let's take a look on the inside here. I've already filled in our definitions for you to try to make things a little easier so you didn't have to sit here and write them all out. So increasing. So our increasing graph means that as you move through the graph from the left to the right, the graph rises. So left to right, always going left to right, just as if you were reading a book, then your graph is rising. And also the other way of phrasing it is as X values increase, your Y values also increase. So as our domain increases, our range is also increasing, kind of throwing our other vocabulary words in there. So an example of an increasing graph, a line with a positive slope value to it, that would be an increasing graph. So that is increasing for the entire graph here, because as I start on the left side, I move my way over to the right, my graph is increasing. So next we have decreasing. So our decreasing, just opposite, we move left to right again, the graph is falling. So again, when we move left to right, our graph is falling. So our X values, also known as our domain, increase, our Y values or our range decrease. Our X values are always going to be increasing here because we are going from the left to the right. So those will always be increasing. So here's my picture for a decreasing graph. So as we go left to right, that graph is decreasing. We can also have some graphs that do both. We can have some graphs that have both an increasing and a decreasing piece. So like, for example, our quadratic here. So over here on the left side of it, this side is decreasing as I go left to right. Try to zoom in a little more for you. Because as I go left to right, it's going down, so that side of it is decreasing, whereas though on the right side of it, as I go left to right on the right side, that side is increasing. So whenever we talk about increasing, decreasing, they always want to know that domain interval over when it is increasing, decreasing. So for our linear, that pen doesn't work very well. Our domain interval would be everything. Our linear graph is always either increasing or it's always decreasing. I'll use brown. So my domain interval over where it's increasing, for that first one, over when it's decreasing for that second one, that's a DEC for decreasing. That's going to be everything. It's always going to be increasing or decreasing. Whereas for that last graph, it's decreasing when X is less than 0, because it's decreasing over here in the negative values of your X. But it's increasing over here when X is greater than 0, because those are your positive X values. That is when your graph is increasing and going up. We'll talk about that more with our examples too. Next one we have is positive and negative. So positive, that is our notation for f of x is greater than 0. That is how we say in function notation that the graph is positive. So this is when the graph lies above the x-axis. So in other words, when your range values are positive, that is when we say that the graph is positive. So then our negative, again, there's our notation for it. F of x is less than 0. That is when our graph lies below the x-axis. So our y values, our range values, are negative. So here, whenever the graph is up above that x-axis, we say it's positive. And whenever it's down here below that x-axis, we say that our graph is negative. So again, when they ask us about positive and negative, we refer to the domain values, and we use those domain values to help us indicate when the graph is positive and when that graph is negative. Now, you can never actually include 0, a y value of 0, because a y value of 0 means that it's on the x-axis. So when y equals 0, it's on x-axis, and 0 isn't positive or negative. 0 is one of those special numbers. 0 is never positive and 0 is never negative. It is just 0. It's kind of like that placeholder in between your positives and negatives. So it itself is never actually positive or negative. So when we're dealing with our domain for it, it will never be equal to 0. You're either above it or you're below it, never equal to it. All right. So maximum and minimums. You've talked about this before, but we have two different kinds of maximums and minimums. We have what we call an absolute maximum, and we have what we call a relative maximum. So I'm going to draw a picture of a graph right here. That's going to be an endpoint. That's not going to be an arrow. And then there's another endpoint. Yep, this will work. So if we read through our definition, absolute maximum or minimum are the x values that are the highest or lowest that the graph ever gets. So right here and right here, those are absolute maxes and mins. So this is going to be an absolute max. And this is an absolute min. Nothing will get higher or lower than those values. And then these other two, this one right here and here, that's kind of like a peak and a valley, as we like to call them, for that area. So these are what we call the relative maxes or mins. So this one is relative max. It's high for the area, and this one is a relative min because it's a low for the area, and it makes that curve. It looks kind of like our turning points and our vertexes that we talk about with our quadratics and our absolute values, but they're not the absolute maximum or the absolute minimum. They're just highs and lows for that area. So we call them relative maxes or mins. All right, so let's switch to the other side then. Let's go ahead and do end behaviors first. I'm going to switch it up. We'll go with end behaviors down here at the bottom. So your end behaviors is the direction that the graph is going on both the left and the right side. So let's say, for example, I had an absolute value graph. There we go. I got my absolute value graph. So back in Algebra 1, the way we would write this, Algebra 1, you would say left side is going up, right side is going up. That's how we would write it. And that was perfectly fine for at the time. You were just getting the idea of what is happening. This is what's happening. My left side is following a pattern where it is increasing and is going to continue increasing on that side. And my right side is following a pattern where that is increasing and it's going to continue to increase on that side also. However, we need to change up our notation. So for algebra 2, here's how we're going to write things. So when we are referring to the left side, we say x approaches negative infinity. That's our notation for the left side of the graph. So the way we would write that as far as our end behavior goes is we would say that as x approaches negative infinity, my function, so f of x approaches positive infinity. So that is saying that the graph is going up. So as my domain, my x's go towards the negative infinity, that's the left side. The function itself is going up. That is how we say that. So then for our right side, I almost spelled the word right wrong. We say as x approaches positive infinity. That's our word that we use for the right side. So for this graph, we would say as x approaches positive infinity, the function is also approaching positive infinity. And that is our notation now for saying that the right side is going up. So it's still the same idea. What direction is it going in? We are just changing our notation that goes along with it, and we're getting a little bit more technical with it, if you want to say. All right. So next up, continuous and discontinuous. Again, we talked about this with our piecewise functions. Continuous just means that the graph is all connected. It completely flows. So I'll draw a couple examples of continuous graphs. That's a continuous graph. Quadratic would be a continuous graph. We're very used to continuous graphs. You draw them quite frequently. And then our discontinuous, that is like our piecewise that we were talking about. So that graph there would be a discontinuous graph, and it's discontinuous right here at this point in time. That is where we have our break in the graph. Let's see here, another example of a discontinuous graph. There we go. So I got my little purple lines here. We call this a step function. We don't need to worry about step functions, but it was just another example that came into my head of what a discontinuous graph would look like. Not connected, breaks in the graph, kind of has jumps there. All right. And then our last idea on here, and then we're going to do some examples on that other paper that I gave you, symmetry. So we like to look to see if a graph has even symmetry or odd symmetry. And what this does is it helps us see a pattern, and then that pattern can translate into whatever problem it is that we're trying to solve. So we look for symmetry to help us with that pattern, or we use symmetry sometimes to help us finish drawing a picture of a graph, or symmetry can be used to help us find missing data points that we are looking for. So symmetry has a lot of uses to it. Even symmetry means that the graph is symmetrical over that y-axis. So graphically, a quadratic function there, that has even symmetry. That is symmetrical over my y-axis. Your absolute value graphs would have even symmetry. Pretty much, remember, symmetry from like elementary school means if you fold a piece of paper along that line, which in this case is the y-axis, it's going to look exactly the same on both sides of it. So table-wise, what even symmetry looks like. I'll do -2, -1, 0, 1, and 2 for my domain there. So what even symmetry looks like is -2 and +2 will give you the same value. No matter whether x is positive or negative, you get that same value. So then like -1 and +1 would give you the same value. 0 doesn't have a negative counterpart because, again, 0 is neither negative or positive. So that's what it looks like table-wise. And again, that is very much so our quadratic function right there. So a little note here, positive x and negative x gives the same range values. So kind of connecting to some language from last unit, one-to-one functions never have even symmetry because they would fail your horizontal line test. I'm just thinking quickly in my head, they would never be onto either. So they would just be functions, like our quadratic, absolute value, some quartic that we'll get into later on in the year. Then our odd symmetry. There we go. So for our odd symmetry, it is symmetrical through the origin. Symmetrical through the origin. So this graph, our cubic graph, which we'll talk about more again in the next couple of lessons, that has odd symmetry. That is symmetrical through the origin. I always like to think about it as if I took my paper and I flipped it 180 degrees, it would look exactly the same. So I would take it and I would still have the same function. That's the same graph I had when my paper was right side up. So symmetrical through the origin. So in the table, what an odd symmetry would look like. We'll go again with -2, -1, 0, 1, and 2. So they don't give you the same values like they did in the even symmetry. It would actually give you the negative versions of those. So like, for example, this 2, +2 would give me a +8, -2 would give me a -8. So these values are also negated of each other, just like -2 and +2 are. We'll talk about that more later, but it just means that you switch the sign value. So one gives you a positive version, one gives you a negative version of that number. So positive x and negative x gives you range values that are opposite signs. So again, what that means is if positive x gives you a positive y, negative x would give you a negative y range value. If positive x gave you a negative y range value, then negative x would give you positive. So those signs are always opposites of each other. All right, so let's take a look at that other paper that I gave you for your notes tonight that you're going to cut out and glue in on the page after this. So this one right here, I actually colored on it a little bit. So these are just some examples of some questions dealing with our functions and some of our key features of functions. We will definitely talk about this a little bit more in class. All right, so the first one, I'm going to use different colors because I'm going to be drawing over here on this graph. So if you also have different colors, that'll make it a little easier. So the y-intercept of our function, we just look to the y-axis. Pretty easy. Our y-intercept here is a 2. There is only one y-intercept because it is a function. It can't have more than one y-intercept. State the x-intercept of the function. What is the alternative name for the x-intercepts? This one has 2 x-intercepts. So y-intercept is where it hits your y-axis. X-intercepts are where it hits your x-axis. So this is at 1, 2, 3, 4, 5, -6. 1, 2, 3, and +4. That's where my 2 x-intercepts are. And so then our other names for our x-intercepts are root and zeros. Hopefully you remember those words from Algebra 1. Roots and zeros are also what we call our x-intercepts. Okay, over the interval of -1 to 2, is f of x increasing or decreasing? So there's an example of our interval. It's talking about the domain values because it's got an x there in the middle, so that's how we know that this is going to be domain. So I have to look from when my x values are a -1, which is right here. I'm going to follow the graph until I get to +2. And as I follow that graph, my highlighter is going up. So this is going to be increasing. So from -1 to 2, that graph is increasing. Okay, next question. Give the interval over which the function f of x is greater than 0. What is a quick way of seeing this visually? So greater than 0, remember that means we are looking for when it's positive, because the values that are greater than 0 are positive values. The quick way of being able to see this visually is it's above the x-axis. Okay, so above the x-axis is what we're looking for. This part here, this is negative. This is where I switch, and now positive, 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 until I get back to 0 again. So from my left root to my right root, that is when my graph is positive. So my interval would be either -6 is less than x, which is less than 4 if I was using my set notation. If I was using my interval notation, they would be parentheses, because remember, you don't include where it is 0, because 0 is not positive or negative. Okay, it just starts at that number, and it's everything after that. All right. State all x coordinates of the relative maximums and relative minimums. Label each. So we're just looking for the x portions of those relative maxes and mins. So right here, that's going to be a relative maximum. Here is a relative minimum. And here is a relative max, followed by a relative min right there at the end. So we have a total of 4 of them. So we have 2 relative maxes, 2 relative mins. So let's see here. 1, 2, 3, 4. -4 is one of our relative maxes. And at +6 is our other relative max. So we have 2 of them. -4 and +6. Our minimums are at -1 and +5. Label each. Okay, so relative max, relative min, relative min, relative max. There we go. I labeled all 4 of them. So what are, our next question there, what are the absolute maximum and minimum values of this function? Where do they occur? So the absolute max and min values, when they phrase it that way, what are the absolute max and min values? They want the range or your y value. They want to actually know how high it gets. All right. So let's take a look. Here is, move that down so you can see my graph. Here's my absolute max. Didn't tell me to label, but I am, just to help drive the point home what they are. Absolute min. So here, my absolute max is at 1, 2, 3, 4, 5, 6, 7, 8. So absolute max is at 8. Absolute min is at 1, 2, 3, -4. So my absolute maximum value is 8. My absolute minimum value is -4. Where do they occur? That's where they want the domain or x value of when they occur, or where they occur, I should say. So for this one, my absolute max is at x equals 2. My absolute min is at x equals negative 8. So what is the value? That is the y part. So my 8, my negative 4. Where do they occur? That is the x. And those are little at signs. So at x equals 2, at x equals negative 8. All right. G, state the domain and range using interval notation. All right, domain goes all the way here, starting at negative 8, goes to positive 6. Oh, I'm sorry. So negative 8 to positive 6. Those don't have open circles on the end. Again, they would make it very obvious that it's an open circle if they wanted it to be an open circle. It looks like a circle because remember I circled them. They didn't, I did. So then the range, my absolute min is at negative 4 and my max is at 8. So negative 4 to 8. And again, none of those were open circles. So we're going to have brackets for both of those, unlike question D here, where we had a parenthesis. Okay. H, if a second function, g of x, is defined by this formula here, then what is the y-intercept of g? So this has absolutely nothing to do with the graph, because the graph, as we see right here, which I ended up writing over, that is f of x. I don't care about f of x for this question. I just want g of x. So g of x, looking at the equation, it looks like it's following a linear pattern. So I'm going to distribute that 1/2 so that I actually have my mx plus b here. Mx plus b. So my y-intercept is my b value. So my y-intercept here is 1. I didn't have to graph it, although you could have. You could have graphed it. You didn't have to, though. All right, so go try a couple practice. We're going to talk about this during class some more, too, and get some more practice there.